So welcome back, students. We're going to be shifting gears today. One of the things we're going to be taking a look at today would be what I would call the behavior of gases. Hey, behavior of gas, strange how my brain works. That kind of reminds me of a dad joke. So where do turtles get their gas from? The Shell station. Anyway, our goals for today are very specific ideas. Some of them are really factual type things, and then there's a few skill related things. Let's shut this guy off. We don't need to keep hearing that. Okay. So specifically what we're going to look at today is what we're speaking about, the state of matter, gas, not gasoline. I'm becoming technologically illiterate here with this phone. Let's shut it off. There we go. Okay, so we want to be speaking of the state of matter called gases today. So we want to talk a little bit about what causes pressure. We want to identify some factors that change or influence pressure. I'd like you to understand that here on Earth, we have what's called air pressure, where it comes from. Identifying that one thing that's really confusing about pressure is there's lots of units of measure to measure it, kind of like inches, feet, miles, or all these units to measure length. There are a lot of units for measuring pressure, and we'll probably stick to some of the common ones for our work that relate more to maybe a laboratory setting or chemistry style setting. But I need you to be aware there are many kinds of units of measure. Some of you being students studying at a technical school, you probably know of a unit called PSI, pounds per square inch, maybe even athletes. If you remember Deflategate from the Tom Brady episode, inflating a football up to a certain pressure, typically in a unit called PSI. But, there's something called ideal gas behavior. I'd like you to have an idea what that means, and how it relates to volume and pressure. And then finally, the last thing is a skill. We to be able to use what we call Charles' law, or if we're going to say it in French, Charlet, and Boyle's law to relate to the volume of a gas, how pressure and temperature influence that. So those are our very specific goals for today's lesson. Let's get right underway. So what is it that causes gas pressure here on Earth? Well, it's kind of like Patrick Starfish says, particles. So it relates to particles. The presence of particles can create gas pressure. So what we know, it's actually not just the presence, it's the collision on the walls of a confining vessel or a container. As the particles bounce around, they end up bouncing on the outer walls of the container. And the more frequently they bounce on those outer walls, the more pressure they create. So these collisions with the outer walls of the container create what we call pressure. And what we can do is we can kind of realize that we can change the frequency of those collisions by a number of factors. So one of those factors would be to increase the temperature. As we increase the temperature of particles, they'd move faster. That would make more frequent collision with the outer walls, increases the pressure. Very logical. Increasing the number of particles, add some more particles into that little space here. As there are more particles, that's going to get more frequency of collision on the outer walls because there's more particles available to collide. This should sound familiar to our ideas that relate to collision theory. And then finally, decreasing the volume of something like a container. If we take the same number of particles but force them into a smaller space like we have here, we end up with a greater pressure because of a more frequent number of collisions. So we have factors that affect gas pressure. Generally, these are three commonly thought of factors. Okay, let's get rid of my face. I get tired of looking at that while I'm speaking during these. There we go. So here we go, we move forward. So here on Earth, we have gas pressure for a very specific reason. Well, here on Earth, we have gravity. And as a result, one of the things that we also have here on Earth is an atmosphere. Atmosphere is made of particles, primarily nitrogen and oxygen, although there are some other particles there. Well, what we know is that gravity pulls these particles downward. And more of the particles accumulate down here near the surface because gravity is pulling them downward. Now, they can't all get down here because there's not room for all of them. As they bounce and collide, some of them get projected back upward. So one thing that we know that happens, however, is as we increase in altitude, you probably have experienced this if you ever flying, you can feel the air pressure in your ears actually change. And that's because there's less particles present up here on Earth. So down near the surface of Earth, down near what we call sea level, we have higher pressure because there are more particles stacked above us. As we rise and rise and rise and rise and rise and rise and rise, now there would be less particles stacked above us, less air pressure. So we like to say the air is thinner when we increase in altitude or height. Some of you have probably experienced that, maybe traveling while driving up a very steep hill in the car. You can sometimes feel that air pressure changing, the air pressure in your ears sort of trying to balance itself out again. So air pressure. Here on Earth, gravity, if we wanted to view it maybe a different way, this might be a good way to view it. So here we got a situation, and we got our air molecules, mostly nitrogen and oxygen, pushing downward. And that nitrogen and oxygen, primarily our atmosphere is about 78% nitrogen, about 21% oxygen. And that oxygen and nitrogen get pulled downward by gravity. And if you were down here, you would sense greater pressure where the X is than if you were elevated, maybe near a mountaintop up here. So the weight of the air above us, as gravity pulls it down, creates what we call pressure. You may notice this if you ever swam to the bottom of a very deep pool. You can feel the pressure in your ears, maybe in the diving end of the pool, where the pool may be like 12 to 14 feet deep. You can actually physically feel that pressure above you. It's because there's more molecules stacked above you. Same thing happens with gases. So what we do know is it has a definition. We've defined pressure here on Earth with a unit called an atmosphere, abbreviated ATM. So 1 atmosphere is defined sort of as, if we were to take a square down here at the surface, build a square that's 1 meter by 1 meter, and raise that square upward all the way up to the top of the Earth's atmosphere, all of those molecules stacked above us create a pressure in that 1 square meter of area that we call 1 atmosphere. So if we start at sea level all the way to the top of the Earth's atmosphere, we end up with a unit of pressure we call 1 atmosphere. So there's lots of other units for pressure. The one we'll more commonly use with atmosphere will be something called kPa. It stands for kilopascal. Some of you may be familiar with a unit called PSI. Usually in our automotive trades, we inflate tires or bicycle tires, car tires, to a certain pressure, usually rated in PSI. And if we ever watch the weather, sometimes we'll hear inches of mercury. They'll say the barometric pressure today is 29.91. Well, that's equivalent to 1 atmosphere. So these are all values equal to 1 atmosphere of pressure. That value that's equal to that column of air from sea level all the way to the top of the Earth's atmosphere, the force that it pushes down with creates that pressure that we know as 1 atmosphere. So there's lots of common units for pressure. One's called the atmosphere. It's a metric unit, comes from the metric system. We just described where it's defined from. 1 square meter of air from sea level to the top of the Earth defines what we call an atmosphere. There's another unit, a metric equivalent unit called the millimeters of mercury. One called Pascal is a unit. Pascal comes from the international system, or the SI unit. So what we notice is Pascal's a really tiny unit, so we tend to use what we call kilopascal, which means 1,000 Pascal. So the 2 commonly used pressure units we'll use will be atmosphere or kilopascal, kPa or ATM. We're going to be aware that these other units exist, but primarily for our work, we're going to work within units of measure that are a little bit more common in a laboratory setting. Okay, so atmosphere, kPa, inches of mercury would be an English unit. We might hear this on the weather forecast. 1 atmosphere is equal to 29.9 of those. So I'm not asking you to memorize these guys down here. I need you to be aware that there are lots of ways to describe an equivalent amount of pressure to 1 atmosphere. Certainly, I could have you convert from atmosphere to PSI, from atmosphere to kPa, atmosphere to millimeters of mercury. That's not really what we're getting at in today's lesson, but be aware that there's many ways to describe air pressure. We're going to stick with atmosphere and kPa for most of our work. Okay, so next item on our list is we have this behavior that we like to say for gases. Well, if you remember, early on in our experience together, we used a kind of a key term. I like to call the key term IMF. It stands for intermolecular force, which means attractive force between molecules. Gases, we often think about gases as having limited or no intermolecular force. Truth of the matter is they tend to have some, but it tends to be insignificant in many cases. So we say that gases behave in an ideal way where they don't have intermolecular force that really matters. So in order to understand ideal gas behavior, we sort of ignore that there actually is some IMF for gases, but it tends to be insignificant in many instances. Instances where it would become significant would be when the temperature is really, really low for a chemical. That kind of makes particles come closer together. And now they can feel those intermolecular forces with greater presence. Also, when gases are under high pressure, we push those particles closer together. They can feel or experience that IMF because they are stacked closer together. So ideal gas behavior kind of allows us to think about gas molecules not really having intermolecular force. That's why we call it ideal. It's not necessarily a real situation, but it is something that we can use to predict the behavior of gases. So one thing we could know would be if we were to heat up gases in a vessel that has this little piston that could either move up or down, right? Piston moves up or down. We heat that gas, these molecules will move rapidly and they'll start pounding on the bottom of this little cylinder plate. And what that'll do is push that cylinder plate upward and it changes the volume of the gas. And what caused that was the gases were moving faster because they were at a higher temperature. So as long as gases have ideal behavior, this is a very predictable thing. Another thing that we can say that is very predictable is it doesn't really matter what the identity of gases are. As gases occupy a container, the only thing that influences the pressure inside the container is the number of particles. The identity, being oxygen or nitrogen, really doesn't matter. What matters is how many total particles are present. Now, again, we're speaking only about ideal conditions. So ideal gas behavior allows us to do two things: make accurate prediction of gas volumes, right? Gas volume can be changed. We can accurately predict it when we know that IMF is not really a factor. And it allows us to understand that the pressure of a mixture is related only to the number of gas particles present. Remember at the beginning of the presentation, Patrick Starfish, particles. So the more gas particles we have, the more collisions on the outer wall, the greater the presence of pressure. If we notice, we took the oxygen particles and the nitrogen particles from two separate containers, put them together in one big container, and the pressure increased. Just because the number of particles went up, not because of the identity. Okay, moving forward, what we're going to take a look at, we're going to take a look specifically today at two ideas. Eventually, they'll become what we call the combined gas law. Today, we're going to look at something called Boyle's law and something called Charles' law. Charles' law allows us to relate what we call volume, V, and temperature of a gas. Boyle's law is going to allow us to relate pressure, P, and volume of a gas. So their relationships, one thing we're going to need to keep in mind is there is a temperature scale. In order for these relationships to exist, we have to use this temperature scale called Kelvin. So if we're given a temperature that is commonly measured in a laboratory setting in degrees C, what we're going to do is we're going to take degrees C and we're going to add 273 to it. I like to say this: to get K from C, add 273, right? So to get K from C, we add 273 to it. that will allow us to have a Kelvin temperature. So somebody might wonder, well, why does that matter, Mr. Brewer? Well, here's why it matters. Celsius temperatures can be negative amounts, and we're looking at mathematical relationships. And what we're going to end up finding out is that the temperature controls the volume of a gas, and we can never have negative volume. So what we end up with is negative amounts unless we deal with Kelvin. So that may be an oversimplified form of reasoning, but in general, it's the truth. So let's get underway with what we call Charles' law first. So Charles' law, in order to deal with Charles' law, I just made this statement. We're going to have to remember temperature must be in Kelvin. That means we take our Celsius amounts and we convert to Kelvin by adding 273. When we deal with Boyle's law on pressure, we just need to be aware that there are various ways of recognizing pressure. Most commonly for our work, we'll probably see kPa, kilopascal units, or ATM, atmosphere units. So here we are, we're looking at Charles' law. We're looking at a situation. Charles' law looks like this. V1 over T1 equals V2 over T2. It stands for the volume of a gas is related to its temperature, but that volume is going to change when its temperature changes. So this is what Charles' law is about. Actually, Jacques Charlet was an avid balloonist, and he was one of the people that began to ponder about this relationship and investigate it further because of his interest in ballooning, hot air ballooning, I'm saying. So we're moving forward here. We have a situation, a context. The volume of a gas in a container was 0.75 liters. We recognize volume by looking for liters, milliliters, those sorts of things. And it was in the room at a temperature of 18 degrees. So our original volume, V1, 0.75, our original temperature, T1, 18 degrees. When we look at the volume of the gas, we want to know, predicting what the volume of the gas would be if the temperature went up. Now, you probably know if we took a balloon and we put it in the oven, the balloon would expand in size, and that's because the particles move more rapidly. They collide with the outer wall of the balloon, and the balloon expands. So we want to be able to make some predictions. So we got some plug and chug style math. We're going to plug in for V1, our initial volume, 0.75 liters. We're going to place that over the initial temperature. Hey, Mr. Brewer, the initial temperature says it's 18 here. Well, how did I get 291? Well, here's what I did. I took 18 and I added 273 to that. So 273 plus 18, right? That adds up to 291. So we must use the temperatures in Kelvin. So 0.75 over 291. Well, the context says that our temperature changed. So let's clear our drawing up a little bit. So we're going to set that equal to our new conditions. We want to predict what the volume, the new volume would be. Well, we don't know the volume, so it's our unknown. Let's keep it as V. We know the new temperature was 92. So why am I writing 365? Because 273 plus 92 makes 365. Now we got what we call simple proportion. The easiest way to solve proportions, cross multiply 291 times V, 0.75 times 365, rewrite the equation. 291V equals 273.75. Let's divide each side by 291 so we can isolate V, and voila, V, or volume, now becomes 0.94 liters. Notice the volume started at 0.75, but it increased to 0.94. Well, that makes sense, folks, because the temperature went up. So an increase in temperature caused an increase in volume in this case. Let's take a look at a second example. So here we're looking at a different context, and we want to read carefully. Again, it's still Charles' law, a relationship between volume and temperature. It said at 125 degrees Celsius, a gas has a volume of 27 liters. What should the temperature of the gas be if it was cooled to create a new volume of 24.6? So plug and chug style math, our initial volume, V1, 27 liters. Our temperature, 398. Well, it was 175. Well, how did we get 398? We got 398 because we have to have temperature in Kelvin. So we added 273 and 125 to get 398. We're going to set that equal to V2 over T2. Well, now we want to know what should the temperature be. So now our T is our unknown. Our V2 becomes 24.6, our new volume. We're going to put that over T because T is unknown. We're going to cross multiply. 27 times T becomes 9,990.8. Divide each side by 27. Voila, new temperature, 363 K. Notice the temperature we solve for is in a Kelvin amount. So it's in a Kelvin amount. Well, that's not a big deal. If we wanted the Celsius amount, we'd do the opposite to what we're seeing here. So what we're seeing, sorry about that. The ice cream man's coming around and the dogs are getting excited. Not that they get ice cream. Anyway, 363 Kelvin would be equivalent to 90 degrees Celsius. All I did was the reverse of converting Celsius to Kelvin. We went backwards. We went from Kelvin back to Celsius by subtracting 273. So let's see if this makes sense. Our gas cooled from 125 down to 90. When it does that, the volume goes from 27 liters to 24.6 liters. That makes sense, folks. So Charles' law, a relationship between volume and temperature. Let us take a look at the next law, relates to what we call Boyle's law. Boyle's law does not involve temperature. In fact, Boyle's law assumes that temperature is constant. So if we hold the temperature constant, we can make predictions about what happens with volume and pressure. So point to note here, doesn't really matter what volume units or pressure units we have as long as they're consistent. If we're given two volumes and they're both in liters, that's great. If we're given two pressures and they're both in atmospheres or kilopascals, also great. So we can keep the units that we're dealing with in the specified form that we're given, so long as they are consistent. I'll point that out in the context we have here. So here we got a context. It says the volume of a gas under 1.35 atmospheres of pressure was 69.3 liters. So the air pressure, 1.35 atmospheres, is squeezing on this volume and holding it in place at 69.3 liters. They want to know what should be the volume of the gas when the pressure rises to 2.68 atmospheres. Now it's squeezing harder because there is a greater pressure. So we should think greater squeezing is probably going to shrink our volume. We're pushing those particles closer together. Well, let's plug in our context. V1 and P1. The initial volume in liters, 69.3 times our initial pressure. In this case, it's in atmospheres. Notice our two pressures are both in atmosphere amounts. That's what I meant. As long as our pressure units are identical, there's no need to convert them to some equivalent amount. So our atmosphere pressure, we can use that. Okay, so V1, P1. V2, we want to predict the volume, so we don't know the V2. So we're going to keep that as unknown V. And the new pressure is 2.68 atmospheres. We've just plugged into Boyle's law. We're going to clean this up by multiplying each side a little bit. 93.555 is equal to 2.68 V. Obviously, we want to solve for volume or V. Divide each side by 2.68. That's going to arrive at a new volume, 34.9 liters. Let's see if this makes sense. The pressure started at 1.35 atmospheres and we had 69 liters. But the pressure went up, so it squeezed harder on these particles and made the volume shrink as a result. 34.9 liters. Makes sense, folks. I like it. Okay, final example, Boyle's law. So here we got a gas that has a volume of 32.6 liters under a pressure. It doesn't matter. The pressure is now in kPa, just a different unit for pressure, kilopascals. So if a gas had a volume of 32.6 liters under this pressure, there's our V1, our initial volume, and our initial pressure, our P1. Now it's just a kilopascal amount instead of an atmosphere amount. We're going to look for V2. V2 is our second volume, right? 27.2, but they said the pressure changed. So we want to know or solve for that pressure. So we'll keep that as unknown P. We're going to multiply V1 and P1. We're going to multiply V2 and P. And we're going to get 3,449.08 is equal to 27.2 P. We want to solve or isolate for P. We're going to divide each side by 27.2. And we're going to get a new pressure, 127.8 kilopascals. Let's see if this makes sense. So we had a volume of 32.6 liters under a pressure of 105.8 kilopascals. Look what happened to the volume, folks. The volume went down. Well, in order for the volume to go down, that pressure better go up, because that's going to squeeze harder on these particles and cause the volume to shrink because they're being squeezed with greater force. So this wraps up our study today on ideas that relate to the behavior of gases. And Boyle's law and Charles' law are the two mathematical concepts. The rest of today's lesson goals focused mostly on things that were related to remembering. And if we went back to take a quick look at what those goals were, again, at the beginning of the slides in this unit, or the segment of this unit, we see there's a number of things for us to try to recall. What causes the pressure related to gases? We talked about particles. That's not a one-word answer. It has to be particles colliding with the outer walls of a vessel, like a container. What would be the factors that influence changes in gas pressure? Well, we looked at those, right? More frequent collisions, either by changing the temperature, increasing the number of particles, decreasing the volume. Why do we have air pressure here on Earth? Well, here on Earth, gravity causes air particles to be pulled downward, and down near the surface, there are a greater number of particles stacked up on us than if we were up higher in maybe like a mountain setting. So we end up with something called air pressure. So ideal gas behavior, we say that when we sort of ignore the effect of intermolecular force, even though gases have minimal intermolecular force, what can happen is when a gas becomes pressurized or very, very cool, that IMF actually becomes somewhat significant. But if we're going to talk about ideal gas behavior, we sort of have to ignore that. So that wraps up or concludes today's lesson on the behavior of gases. Until the next time, folks, I bid you peace.